Hi class, this is Dr. Jones and I wanted to show you how to graph the data for the experiment that we did on last night. So I'm going to start off by putting in some of the variables. Put temperature in centigrade or Celsius in the first column, and I'm going to put volume in the second column. And this is a problem that we have because the Excel is actually designed to recognize a C in parentheses. It's the copyright signal, so I'm going to have to add the percent. I'm sorry, the degree symbol. So degrees Celsius or centigrade, and here's our volume, and of course this is in milliliters. So I'm going to enter in the data that I have, and we're going to have some error because if you recall, you were supposed to have recorded the temperature to 1/10 of a degree and the volume to 1/100th of a degree, and because most of the class didn't do that, even though you were instructed to, there's going to be quite a bit of error associated with your experiment, so keep that in mind. And in this set of data, of course, you'll see that I have skipped the 80-degree point, and that's because the 80 was over the 10 milliliter mark. So I'm going to enter in the volumes, which are in milliliters, and the first one at 75 is 9.4, 9.9, 0.4, 8, 7.8, 7.6, and 5.4. Okay. I think I entered that in wrong. That should be 5.4. Okay. So those are my volumes in milliliters. And the first thing that it tells us to do is that we need to do a corrected volume. So this is our corrected volume, which is also in milliliters. And it tells us to take our volume and to subtract 0.2 from it. So I'm going to do a equation. Okay, so I want it to do a calculation. I click on the volume, I'm going to subtract 0.2, and I'm going to copy that function down, and it does it for me automatically. Okay, and you'll see I've already formatted these so that they have the correct decimal places as indicated in the experiment. Okay, so it tells me that I need to do a corrected pressure that I need to use in calculations. And so to do the corrected pressure, okay, so this is pressure corrected. It tells me that I need to take the pressure that was recorded, which was the 762.3, plus the millimeters of water that were measured, okay, and I think you guys said it was 21. Again, you should have went one decimal place past that, but you didn't, so it's going to cause us error again, times 1 divided by 13.6. So that's our corrected pressure that we're going to use in our calculations. Okay, and the first thing that it tells us that we need to do with that is we need to calculate the number of moles of air. And so to calculate the number of moles of air, we have to use the volume that it gave us at 0 degrees Celsius, which was 5.4 milliliters. And we have to use the ideal gas equation, and we have to solve for the number of moles. So if I rearrange that equation, then the number of moles is equal to the pressure, which we just corrected for, okay, times the volume. And because it needs to be in liters, because it's the ideal gas equation, I have to move my decimal point over. So that's going to be 5.4 e negative 3 Okay. And then I have to divide that by R. And because the pressures in millimeters of mercury, the R that they give us is 62.4, which we use with that particular value of pressure in millimeters of mercury. And we divide it by the absolute temperature. Since the volume should have been the same at 0 degrees Celsius, we're going to divide by 273.15 because that's the temperature at 0 degrees Celsius in Kelvin. Okay. So that calculation gives us the number of moles, which is the next thing that we're going to need to do our calculation. So now that I have the number of moles, what I can do is I can actually calculate the partial pressure of air using the ideal gas equation. And so what I'm going to do is I'm going to put here that this is going to be the partial pressure of air, and it's in millimeters of mercury. Okay. And what I'm going to do is I am also going to do another column. So I'm going to insert a column here actually. And this is going to be the temperature in kelvins because I'm going to need to use that in the graph and also in this equation. So this is the temperature in Kelvin. And that, of course, is equal to the recorded temperature plus 273.15. And since I want that to be the same, I'm going to pull that down. Okay. So now I have temperature in Kelvin, and I want to calculate the pressure of air. So I take the rearranged ideal gas equation, which is PV equals nRT, and solving for the pressure is going to be nRT over V, which is the volume in liters. So I'm going to say this should equal to N. So I'm going to click on that and I'm going to lock it in place. And so I'm going to hit F4, which is one of our function keys. And if you're using a Mac, it's Apple T. Okay, Apple T does the same thing. It should look like this. So it should put dollar signs around whichever cell you have your moles in. So that's N times R, which is 62.4, times T, which is the absolute temperature, divided by the volume in liters. And so I'm going to do open parentheses. I'm going to click on this, and I'm going to see if it'll let me do E negative 3, because if it will actually let me, it won't let me do that. Okay, so since it won't let me do that, I'm going to have to actually divide by 1,000. That's the same thing. So I'm going to have to divide that number by 1,000. And that gives me the partial pressure of air. Okay. And so what I'm going to do is I am going to actually drag this down, and it does all of the calculations for me. Okay. Now, in my next column, I'm actually going to have the partial pressure of water, which is what we're interested in. And this, of course, is also in millimeters of mercury. And so to get the partial pressure of water, I'm simply going to take the total pressure, okay, which is this pressure, and I'm going to lock it in place because it's the same. And I'm going to subtract the partial pressure of air because the total pressure is the sum of the partial pressures. That's Dalton's law of partial pressures. In this case, we only had two things that exerted pressures, air and water. So that is going to be the partial pressure of water. So I need to take the natural log of that partial pressure of water. So the natural log of the partial pressure of water So to do that, I do the at symbol, type LN, open parentheses, and I click on the partial pressure of water, close parentheses, and I hit enter. And so when I do that, I can drag this down. Okay. and it will give me the partial pressures of water. And I didn't drag it out to the last cell because that's actually not one of our points, so that actually doesn't matter. And I also need 1 over the temperature, which is in inverse kelvins. And that should not be an equation, so it shouldn't be an equal sign there. But this should be an equation, so this is just 1 divided by the absolute temperature, which is in this cell. So I click on it, I hit enter, and I drag this down. So now I have the equations for that. Okay. So what I'm going to do next is I'm going to graph. And so I'm going to click off my values. I'm going to insert a scatter with marker, right click, and go to select data. Or if you're in a Mac, you're going to click on it and then go to the menu and go to select data. I want to add something, and the X values is going to be 1 over the temperature. Okay. Y value is going to be the natural log of the partial pressures. And I do OK and OK. And so there is my graph. It looks relatively linear, okay, which means that the relationship that we talked about in class is a true relationship, even though I think that we're going to have a lot of error because we didn't follow the directions. So I right click, I add the trend line, and in my options for trend line, I display the equation on chart and I display the R squared value. When I do, I get these values. So R squared should be close to 1. It's relatively close to 1, but you can see that some of the points don't lie on the line. Excuse me. And we have y equals to this equation. Now, according to what we've learned, the delta H of vaporization, okay, is supposed to be calculated by multiplying minus the slope times R. And R is 8.314. Multiply this times minus the slope, and the slope is 2416.8. And that gives me a value that's actually in joules per mole instead of kilojoules per mole. And so I didn't put in minus the slope, I put in the slope, I'm sorry. So if it's minus the slope, that's going to be a positive value. And so that gives me a value that's in joules per mole, not kilojoules per mole. And so to get the value in joules per mole, what I need to do is to take the value I just had and I need to divide that by 1,000. And so when you do that, you get a number that is about half of what it should be, which is a 50% error in this particular case. And again, that's mainly because we didn't follow the directions. That is, we did not record the temperature to the nearest tenth of a degree, which actually makes a difference. And we didn't record the volume to the nearest hundredth of a degree, which makes a difference because we're dealing with natural logs. And when you deal with natural logs, those things are much more significant. But that is the main methodology in graphing the data from the experiment. Let me know if you have any questions.